Okay, so previously we were looking at the definite integral. And in this unit, we start now looking at applications of the definite integral. And the first application we want to look at is finding the area between two curves. Well, in fact, actually, we're going to start by finding the net signed area between two curves. So let me specify what I mean by those terms. If we look at the area contained between the red curve and the blue curve here, we can see that some of this area is below the x-axis and some of it's above the x-axis. Area which is above the x-axis is going to be positive. But the area below the x-axis, if we take it as the rectangles being in negative area, this would give us a negative net signed area. So if I try and calculate the net signed area of this purple region, I'm going to have a positive number added to a negative number, and so this negative area is going to detract from the overall area. That means if I want the actual whole area of this, I have to figure out this area, then I have to figure out this area and multiply by -1 and add it to that area. That's a more difficult process, and we'll get to that later. But for now, we're going to content ourselves with just finding the net signed area between these two curves. And finding the net signed area between two curves is fairly straightforward. The formula is given here. And all we do is we take the definite integral from the left endpoint across to the right endpoint of the top function minus the bottom function with respect to x. We anti-differentiate that, of course, and we plug in the upper and lower limit of integration and subtract, and that will give us our value. So let's take a look at an example and see how this works. So we start by considering the area between the curves y equals x cubed and y equals the cube root of x. In questions involving area and net signed area, it's very important that we always start out with a sketch. So I've made one here. Make your sketch nice and big so that you can see what's going on. And remember to shade in the area that you're interested in finding. So here, we want to find the area of this red shaded region. Well, in order to find that area, the first thing we're going to need to do is decide what are the limits of integration. In other words, we're integrating from where to where. It seems pretty obvious that this one's 0. We'll test that in a minute to make sure. But we got to figure out what this point of intersection is. So in order to find the points of intersection of two curves, we set the two curves equal to each other and we solve. So in this case, we would have x squared equals the cube root of x. And if I cube both sides of this, I'm going to be left with an x here. And if I cube x squared, I'll have x to the 6th. If I now subtract the x over, I got x to the 6th minus x equals 0. I can factor out an x, and I'm left with x times x to the 5th minus 1 equals 0, which tells me that either x is 0 or x is 1. The 0 confirms what I see here in the graph. That's my x equals 0, and this, therefore, must be x equals 1. So we want the area between the curves cube root of x and x squared on the interval 0 to 1. So we do exactly what the formula up here says. We're going to integrate from the left, which is 0, over to the right, which is 1, of the top function. Now my top function, I can see here, is the cube root of x. Minus my bottom function is x squared. And so my formula becomes area equals the integral from 0 to 1 of the cube root of x, which I'm going to write as x to the 1/3, minus x squared with respect to x. And now all we're left to do is solve this definite integral, and this goes back to what we've done previously. So you'll remember, in order to solve this, the first thing we need to do is anti-differentiate this. So we say x to the 1/3 must have started as x to the 4/3, and I'll need a 3/4 out in front to balance that. X squared must have started as x cubed, so I'll need a 1/3 to balance that. And I'm evaluating that from 1 to 0. In solving definite integrals, it's always a good idea to set up two sets of brackets like this, because what we're going to do next is we're going to substitute the 1 in, and then substitute the 0 in, and subtract. And it's very easy to make arithmetic mistakes when you're dealing with all of these negative numbers. So if I put a 1 into here, I've got 3/4 times 1 to the 4/3, which is just 1, minus 1/3 times 1 cubed, which is just 1. And in this case, it's quite easy because if I put a 0 in here, it becomes 0. If I put a 0 into the second term, it becomes 0. So this whole thing is just 0. So I'm left with 3/4 minus 1/3, which is 9/12 minus 4/12. Which gives me my final answer of 5/12. Okay, I can check this in the calculator to see if what I've done is correct. So let me get the calculator up here. And what we'll do here, of course, is we'll start by graphing these functions. So let's go to my editor, and I want x to the 1/3 power. That's my cube root function. And I want x squared. So that's the two curves I'm looking at. This is not a very friendly window, so I'm going to stretch this up so I can see it a little bit better. That's a little easier to see. And I might turn that bottom number down a little bit because I'm not really interested in what's going on down there. So now I got a better view of this. X squared is my red function, that's my bottom function. Cube root of x is my blue function, that's my top function. And I wanted to get the area between these two. So if I want to test this on the calculator, if I want to check my answer, I can do this by going into the menu, analyzing the graph, and what I want to find is a bounded area. So I bring this bounded area function up, and it's asking me for a lower bound. Well, my lower bound is this point of intersection right here at 0. So I'll click that. Now it's asking me for an upper bound. My upper bound is this point of intersection up here. I'll click that. And I see that my answer is decimal 417. So the calculator is telling me that this area is decimal 417. It'd be great if that was the same answer I got. The answer I got, when I go back and look, was 5/12. So the only thing left to do is to see if 5/12 equals decimal 417. And I can just go to a different window here, and I can evaluate 5/12, and it is in fact decimal 417, so our two answers agree. So once again, in summary, to find the area between two curves, I take the integral from the left bound to the right bound of the top function minus the bottom function with respect to x, and that will give me the net signed area. Now in this case, because my whole area was positive, the net signed area and the signed area are the same thing. But that won't always be the case. And in further examples, we'll look at the difference between finding area and net signed area.